All right, it's my pleasure to introduce Professor Stephen Boyd. It's kind of like introducing Barack Obama to this community. You already know him. You already know him from his many books, perhaps in particular the book on convex optimization, which has been life-changing. Actually, how many of you have read that book? Okay, how many of you have it within arm's reach of your desk? Oh, not right now. How many of you have used CVX Pi? Okay. How many of you have watched his free online lectures? Okay. I've had the privilege of getting to know Stephen Boyd, and so his free online lectures are super entertaining, and it was only until after I got to know him really well that he was holding back in terms of his humor and personality because it was being recorded. He has energized generations of students. Actually, back when I came to Stanford in 2013, I told people at MIT that I was going to Stanford. Well, one person at least said, "Oh, they have Stephen Boyd. Stanford is really good." So the entire reputation of this university is upon Stephen's shoulders here. Yeah, I'm super grateful to have gotten to know him. He's been a professor here in electrical engineering since 1985. So let's welcome Stephen Boyd.
We gotta take this off. Thanks, Michael. Oh, let's see. Yeah. Was that is there a USB-C?
There's a adapter.
Okay. Let's see. Not quite sure why this is not syncing here. We did test it earlier and it was working.
It took a few minutes.
Okay. We'll just wait then. Aha. That took a lot of time to think, right? That's There we go. Perfect. Thank you for the very nice and way overblown introduction. Thank you very much. I'm extremely happy to be here. This is actually my first actual technical talk in, I don't know, like 2.5 years or something like that, which is crazy. So I've given a whole bunch, and it turns out it's actually not that much fun to sit in your basement and look at your laptop and talk about linear algebra or something. It's just not that fun. Anyway, so I'm super happy to be here.
Would you like a microphone that you can walk with?
Actually, I wouldn't, because
You stay behind the microphone.
What's that?
Stay behind the microphone.
Is that for your recording? Because
Yeah.
I can actually project to the back, I'm pretty sure.
It's everyone that's watching online.
Everyone watching online. Ooh, you wouldn't happen to have do you have a little wireless lavalier one?
Just behind the.
Ooh, okay. Okay. So you've severely cut my radius down to this or something like that. That's okay. I'll make this work. That'll be fine. Although there should be some mystery, right, for the people online, right? Like what do you say? What do you say? Okay. Anyway, I have to say, I also never thought I would ever give a talk at the Elks Lodge. But now there's a lot of other things I thought never happened. Most of them very bad, actually. But this one is not, right? Okay. So what I'm going to talk about is actually. It's extremely simple, so please don't try to read anything deeper in it. It is not deep in the slightest. I'll express some opinions, Some will be controversial, but I'll mark them as such. So, so just to give a rough idea about the talk, it's just basically at the high level. So it's ideas only. I mean, there's basically no math. Like I said, I'm going to give some opinions. Also, I'm not going to slow down to say who did what when, because I'm going to be talking about the work of probably hundreds of people here. So whatever you do when we get to the questions, please don't say, oh, well, your method X or something like that. Please don't, because I'm actually talking about the work of literally hundreds of people, many right here, right now. So yeah, and also it's not going to be entertaining, so sorry. But I figure you have lots of people here who do stuff that is fun and interesting and cool, like with robots and stuff. So I feel like you're going to get enough entertaining before the conference is over anyway. So that's my excuse. Okay. So the first thing I want to talk about is just convex optimization control policies, right? So the basic idea is that a lot of control policies, to evaluate the control policy, you solve a convex optimization problem. I mean, sometimes it has an analytical solution and you don't even think of it that way. But in other cases, you just solve a convex problem. And there's a whole bunch of examples. Let's see if that'll kind of work. So, I mean, there's, a good example would be linear quadratic regulator, right? Like, I mean, no one thinks of it as solving you think of it as multiplying by a gain matrix. You don't think of it anything else, but you're really solving a convex optimization problem. Maybe a Kalman filter, maybe it's not a control policy, but it's the same story. Convex control, well, I'll get to that in a minute. Things like ADP, MPC, and its many pseudonyms like RHC and other things. These all explicitly involve solving an optimization problem to evaluate a policy. It's used basically throughout all quantitative trading. So essentially all quantitative trading, the last thing that happens is you solve a very close to convex problem, which actually takes in all sorts of predictions and forecasts and then emits a trade list. Okay, so that's another area where it's widely used. I think there's all sorts of, there's a bunch of other areas where I think it's actually super interesting. They're kind of, I mean, they're low level, but super important. One is actuator allocation. So this is where some high level thing tells you what forces and torques you should put on something. And then a low level subsystem figures out, depending on the available actuators and things like that, how to do that in some way, right? So it's a small thing. It's just a little part of control technology, but I think it's unbelievably sensible way to do things. Real-time resource allocation is another one. And there are lots of those. Okay, so I'll just go through some examples. I can go fast because I think a lot of these things people know about. And it's just part of it is just to say this has a very long history that goes back basically to like the late 50s, early 60s. So, in traditional quadratic control, you have a linear dynamical system with some process noise. You have a convex quadratic stage cost here, and you want to minimize the average value of that. And the optimal or LQR policy is this. You should solve a minimization problem here. You're minimizing over u. Xt is the state, and you minimize over u. That's a quadratic function of u and x, but when you do partial minimization, which means to minimize over some variables of a function, the result is also, well, for quadratic, it's actually the mapping from there to the solution is linear. And so, normally we just solve this and you work out k, and you say k is the LQR gain, right? So, okay. At the very abstract level, we can talk about just convex optimal control, convex control, right? So here we have some dynamics here, and I have a stage cost G, that's convex. Here, F is affine in X and U. It's basically a linear system, but it can depend on other stuff. I mean, all parts of it can be random and so on. And you want to minimize an average stage cost. And the optimal policy, this is from Bellman, is you should solve an optimization problem where you minimize an expected immediate cost, and then the cost to go from where you land if you choose as action U, right? So this is an optimization problem. And in fact, it's easy to show that for convex optimal control, the value function itself is convex. That's not hard to show. In fact, the Bellman iteration preserves convexity because it consists of two steps: expectation, that preserves convexity, and partial minimization, which is minimizing one group of variables, a function that is convex in all of them, and the result is convex. Okay. So this is another very classic example of a convex optimization control policy. Approximate dynamic programming, you know, is, and I mean, this is interesting, and you can solve this in about for about four problems, right? Like the retirement problem or something like that, and maybe a handful of others, right? But other than that, I mean, and of course, the quadratic case we've already discussed, that's about how many you can do. As a practical matter, this is a whole lot more interesting. So ADP is actually very, very close, and I know many people here know about this, but just thought I'd mention it. What you do is you replace V with an approximation. And there are a couple of, you know, when you choose V hat, of course you'd like it to be close to the value function, V, the true value function, number one. Number two, you want this resulting problem here to be tractable. And I'll take that to mean simply convex, okay? So that's the idea. And this requires only that F is affine in U, so it's input affine and G is convex in U. So that's a huge area, from a practical point of view, unbelievably useful. And now, actually, this is where I don't mind admitting it here, but I actually sometimes admit it in public. One of the dirty secrets is this. It turns out this is a really good control policy, even when V hat is a truly terrible approximation of V, right? So that's something we don't, you know, of course, if V hat is like, you know, plus or minus 5% V, of course it's going to do well. But it turns out you can be way off. It just has to capture the flavor of what are good states and what are bad states. In this case, ellipsoidally, but nevertheless. So that's yeah, we probably shouldn't tell people that. I mean, people outside this community, right? Okay. Model predictive control. I think a lot of people here know about this. In model predictive control, you assume, you know, that the dynamics are affine. So it's linear dynamics, and you have a stage cost. And what you do is you simply roll out the dynamics, you know, out to a horizon. That's what you do. And for all the quantities that are uncertain, I mean, that's what makes all of this interesting, you simply make a forecast, a single forecast, that's all. So, I mean, it just sounds absurd, right? That it sounds like this would never work and stuff like this. These work extremely well, as many of you know, right? So, which is, again, it's the unreasonable effectiveness of a method that appears on the surface to be quite unsophisticated, right? So this is where you would, this is it. And this is used in many areas, and probably a whole lot more. Now, variation on that, maybe one step up, is only slightly less, yeah, it's only slightly more sophisticated, right? So it's multi-forecast model predictive control. And what you do now is you say, okay, fine, I'm going to acknowledge that, in fact, I don't know these future quantities. And so I will ask my forecaster to generate not one, but 10 or 50 possible futures, okay? Then what I do is I make a plan for each of these scenarios, and then I add the constraint that the first action should be the same. And so if you think about it, this is exactly equivalent to the following information pattern in the stochastic control problem. It basically says there are going to be k futures, that's all. You don't know which one it is. But which one it is will be revealed immediately after you take your first action. So that's the information pattern. So that's obviously, like, you know, really a very crude approximation of what you really have. And nevertheless, this works. I mean, I would be shocked if someone could show me some problem, you know, where it's kind of appropriate, where this would not do as well as any method anywhere. I would just be surprised. I didn't believe it, that there is such a thing. No. Okay. Actuator allocation, I think I mentioned this earlier. The idea is this is a lower level thing. It's basically just something where a high level control algorithm would say, for the next 50 milliseconds, please put these forces and torques on this thing, right? And the low level actuator allocation then pulls that off. And it could do things like minimize an objective here, like fuel use or something. You can add a term that makes it smooth, so it doesn't chatter or jump around. And then you respect the constraints, and then this is what maps your local actuator levels into the forces and torques that you're interested in, right? So something like that. So this is super interesting. It works really well. Actually, it works well when things fail. Because, for example, if your third actuator just fails and it's now 0, you just simply plug that into here, and this thing, assuming it's overactuated, if it's not overactuated, this whole thing is silly. But if it's overactuated, it'll going to figure out some other way to put that torque on the car, right? Your right front wheel is over ice, no big deal. It'll use a combination of other things, right? And it'll do it quietly and all that sort of stuff. So, I mean, it's actually, as a practical matter, like, pretty good. This is why you use optimization, I should say. This is exactly it. Okay. Resource allocator, basic idea is you have a bunch of resources and you have a bunch of agents who consume resources. And so I have to decide how much, you know, I could be in a data center and I'm going to decide how much RAM, I/O bandwidth, storage, you know, how many cores Michael gets, right, or something, his process group gets, right? And so for this you have a utility, and he tells me what his throughput or his satisfaction level will be as a function of what I allocate him, right? And then what we have to do is split this up across a bunch of different agents, right? And that's going to be also a convex. And this one is just a very simple one. It's sort of static. It could be static. It could also be dynamic. This could be doing a schedule or something like that. All right, so let's talk about the general form. Well, let's see. A convex optimization control policy is one where it describes the mapping from the state or context to the action that you take, right? And it's basically the argmin, part of the argmin of a convex problem. So I have a convex optimization problem here. And I have a couple of things here. XT, I'm using the traditional thing in control. It denotes a state, but it's also like the context. So that would also include things like the forecasts that are being pumped in, right? U is the variable that I want to minimize over, that I want to choose. That's the actuator, the action. And then theta is a parameter vector which flavorizes the entire policy, okay? And that's actually kind of critical to what we're going to talk about. Okay. So let me just mention a couple of reasons, you know, why, right? Well, the first thing when you talk to people about this, it finally occurred to me after having many strange conversations with people, finally occurred to me that the most complicated thing was actually explaining the difference between a procedural policy and a declarative policy. Like, a procedural policy is if the heat's on and the temperature gets above 73 degrees, turn it off. There, that's a procedural policy. It tells you what to do when, right? Or like some traditional hybrid car energy controllers work that way now, right? You have a long set of if, then, else things, and you go to some decision tree, and you decide to turn on the internal combustion engine or whatever you like, right? So these are procedural. The ones we're going to talk about are actually declarative, which is actually very interesting. It's like declarative programming, and what that means is you articulate what you want and require. Those are the objective and constraints, of course, right? And then what you do is you let the optimization solver figure out how to do it. Right? So, and I had a hilarious conversation with one of your substantially older colleagues. It was very funny. We had a long conversation about this, and it was super funny because I said, look, you say that if you're rolling to the left, you know, tip your right aileron up or whatever, right? And he said, yeah, that's the right thing to do. And I said, yeah, well, so what we do is we say we like flying level, right? So if you start rolling, it's going to do, it knows the dynamics, it's going to tip through. And he said, yeah, but I knew how to do that. And I said, yeah, but you know, you don't know it if your inboard, whatever, stabilizer is floating and blah, blah, blah. And this will just figure out what to do, right? So anyway, all right, so this is one thing. It's actually, so you will meet people who will, especially people who actually build real stuff. They're very comfortable with this, even if the thing is unbelievably complicated, right? Okay. So these are non-controversial examples, I think. I hope they are. So they're interpretable. We know exactly what it does. If I generate a trade list in finance with an objective that has a risk term, a return term, a transaction cost, a holding cost term, and some constraints, I know exactly what it's doing, and it is not going to do something weird, period, right? And by the way, this is a very good way to respect constraints better than simple projection, right? Because simple projection is basically where you pretend there are no constraints, design an appropriate controller, and then simply put in clipping after the fact, right? I mean, that's done a lot, and I mean, I don't know, this is actually better. What's cool is you can also safety fence a controller in this case. So you can put in tons of constraints that you have. Your plan is that they will never be active. You're hoping they'll never be active, right? And they're just there if you get into some weird situation, and this will protect you from doing something very weird. One nice thing is they just completely gracefully handle things like changing dynamics, and availabilities and failures, right? And I'll talk about the tuning later. So one thing you do here is you'd say like, hey, I'm perfectly happy to do a matrix vector multiply, maybe 2 or 3 to update my Kalman filter, and then I'm happy to do that. I'm not going to solve like a QP. You've got to be crazy, right? That's a long, complicated thing. That's just wrong. That's just completely wrong. It's actually relatively straightforward to solve QPs, and you can actually do, even other problems, right? And you can actually make some of these basically division-free, right? So these can be certified, right? In that sense, right? From the things you would actually really worry about, as opposed to the fake things some people would worry about. Okay. Now these are possibly controversial, right? I said, they're never going to do anything crazy like characterize a stop sign as a banana, right, or whatever. It's just not going to happen, right? It's impossible. Like you can't say, whoa, that was a weird, that was a pretty weird like control action. Where did that come from? And you go, I don't know, it's weird. Never saw that. Never saw that happen before. It just can't happen, right? This one is actually controversial. So my claim is parameterizing COCP is better than parameterizing the raw controller or policy. So I actually believe that. By the way, I have friends who don't believe that. And they said, no, we're going to differentiate through the whole thing all the way to the policy, right? In every case where I've looked at that, I can say my experience is that's absolutely the wrong thing to do, and this is better. But there are people I know who still say that this is not the case. Anyway, this is my opinion. By the way, this idea is amazing. You can read about this in books from like 1961, where they actually say things like, when you're doing, linear quadratic control, they'd say your cost functions are not quadratic. These are just knobs that you turn to get a good controller, like period. So you see, and it's a lot easier, for example, to mess with some, positive definite matrices, which are usually diagonal, by the way. It's a lot easier to crank up the third entry in LQR in a diagonal, the 3-3 entry in R, if you think that the third actuator is too big in your simulations. It's extremely easy to do this, right? And my claim is that's better than messing with your gain matrix, right? But there's some who don't believe that. So okay. So let's talk about tuning, or I should say, in the context of this conference, learning, right? So we'll look at it. No. I like tuning better, but that's fine. It's fine. So it's the old word, right? It's from the 1960s. Actually, no, sorry, wait. I think people talked about tuning PID controllers, so that would be the turn of the last century, right? So, okay. So, the way this works is, you build a high-fidelity simulator that uses real historical data, generative model, whatever you like, and then you implement code that enables, that allows you, that evaluates this true performance objectives, right? And it could be based on an entire trajectory. It could be all sorts of stuff. Then you choose a parameterized convex optimization-based policy, and then you tune the parameters. That's what I've called theta, until you're okay with the simulated performance. So that's a perfectly good way to do this. Now, how do you do tuning? Tweaking, by the way, is tuning, except with a slight pejorative hint to it. It just doesn't, it's like somebody just hacking around. Like, how did you pick that parameter to be 12? And they're like, I don't know, seemed like a good idea. Or, my daughter is 12. Or, I don't know, it was things like, that's kind of the picture you get when people think about tweaking. Anyway, fine. Okay. Now, this has been done, this has been done with PID. This has been done in the 19th century for things like PID controllers and things like that. Certainly is done for all modern control stuff. Quote modern. Modern, of course, meaning from the 60s through the 80s, right? Which doesn't make it that modern, but that's fine. And this is fine. And then you just keep doing this until you're either happy or you're bored or whatever. Or you could fire up a derivative-free method, right? Like your favorite Nelder Mead or something, CMAES or whatever these things are. And then you go to lunch. and come back and find some good parameters. Oh, and this is if you had the sense to keep your parameters down to, you know, a plausible number like 5 or 10, right? And not, you know, for example, 10 billion, but okay. So auto-tuning is, you know, this is something like everybody knows about this now. So what you're going to do is you're going to compute the gradient of this performance measure, the true performance measure. That's evaluated in simulation. That could be a whole sequence, right? That could be an entire backtest in finance, where you actually, you go back 4 years, you do daily trading, you solve 1,000 convex problems, and then you evaluate some gross metric of the whole thing, right? And you do something like, it doesn't matter, I've drawn a projected gradient, but you do something, and there's plenty of algorithms that you could use to do this. Now, of course, one issue is that this true loss is like almost never differentiable. That's cool though, because, and this is a huge contribution, I should say, for our friends who do deep learning, is the concept of the quote gradient unquote, which is awesome. So the first time I saw that, I said, that's the best, that is so cool. I said, what does it mean? And they said, well, if it's differentiable, it means it's the gradient. And I said, well, what is it if it's not differentiable? And they go, nah, it's something reasonable. So anyway, it's great. Okay. Now, if you do this, then you can have more than just a few parameters, right? And you have to be careful with a lot of other stuff like overfitting and things. Okay. So we'll look at an example. The example is going to be approximate dynamic program for a box-constrained LQR, right? So we have a linear dynamics, but our inputs are limited to 1 or something like that, and we want to minimize this traditional LQR objective. And the ADP policy is this, and you can see embedded in here, this is something like, you know, a Q function, or that's the value function evaluated at the next point if you took the action U, right? So you solve this thing, that's a QP. And we're going to compare this to a couple things. One is you ignore the constraint, work out the optimal controller, and then just simply clip it at ±1 if the entries are outside the range. And we'll also look at these sort of very fancy bounds you can get, performance bounds, and then also a suggested controller. And you get something like this. So this is iterations of auto-tuning here. And what happens is, so I should say this here is when you do this LMI-based thing, you actually get a lower bound. So it basically says for this problem instance, whatever it is, I don't know what that number is, let's say 78, it says we can prove there's no policy that can give you better than 78, period. That part's actually just a proof. That's not, doesn't, based on simulation or anything like that. The fancy LMI-based thing gives you something like that. And the truth is, somewhere around there is probably what the actual optimal value is. Well, the optimal value is for sure between here and here, and I bet it's closer to the yellow one. Actually, I don't know, but that's my guess, okay? And what you see here is kind of cool, that this thing where you just change you update the parameter, you actually end up learning something just as good as a sophisticated thing where you're solving these giant LMIs and stuff like that, and you get that pretty quickly here. So this is just a baby example. Okay. I want to talk a little bit about now the technology, because there's not really any deep conceptual ideas here. So, but I want to talk about the technology, right? So the first one is like domain-specific languages for convex optimization, and so these are things like, you know, YALMIP, CVX, CVX-Pi, you know, CVX-R, all these things. And you know, at the highest level, the basic idea is this: the contract is this: you accept severe restrictions on what you can type in as a problem. But the flip side is, in the simplest case, we're going to guarantee your problem is convex. Number one, you can't get into trouble there. It's going to be convex by construction. Number two, we can solve it fast and globally and blah, 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 right? So that's actually the deal, right? And so that's how that works. And here's like a CVX-Pi example. And I think a bunch of people here have seen this. I won't go through it. I mean, this is, you declare variables as object, you construct them, you construct parameters, and then, you know, if this is reasonable, it's kind of like Pythonically, it kind of describes what you want to do. Okay, so you describe, actually, this is part of articulating what you want, right? This is, if you think of a declarative policy. Okay, now here's how they work. So first, they take your problem, which is written in one of these domain-specific languages, right? They take that, and then that's canonicalized or compiled into a standard form. Okay, that's the first step. Then you solve that standard form problem, and then you retrieve the solution of your problem from the solution of this standard form problem, right? Now, actually, most people have no idea about this, and that's totally cool. In fact, we like it that way. Most people just make their problem, and they call it a solve method, and that's fine, right? Except when it doesn't work or something. And then we have jokes about it at Stanford, about how a student will say, this didn't work, and then I'll close the door. And I'd say, it always, I'm going to reopen the door, and you say it always works. Just remember, the rule was among the class, you're allowed to say it didn't work. But if you're out in public or if your roommate not in the class asks, it always works. Because that's the story. So we do that. Yeah, okay, fine. Okay. So basically, you canonicalize, you solve, and you retrieve. Okay. Now, it turns out, if you accept some additional restrictions on how the parameters enter into the problem, right, if you do that, then it turns out that the canonicalization and retrieval maps can actually be linear. That means they can be represented by like a giant sparse matrix, right? That's it. Just simply takes your problem parameters, right, which is part of your forecast and your current state and blah, 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 all that, and then maps it in, shoves it into, let's say you're going to solve a QP, it shoves it into the coefficient matrices required by the QP solver, right? So it's actually linear, which is very cool. Okay, and so that simplifies a lot of things, because the one thing I know how to do is extremely good technology for differentiating through linear functions. So that was a joke, by the way. It's fine, whatever. So yeah, all right. So it's actually pretty straightforward. And so this was a few years ago, some people in my group put together CVX Pi layers that would make this differentiating through a convex optimization problem compatible with things like Torch or TensorFlow, these kinds of things. There's a couple of versions, right? And so it really is sort of as simple as something silly like this. I mean, it just kind of works, right? There's a lot of effort to actually pull that off, but in the end, it just kind of works. What's weird about this is this same form, which is a linear canonicalizer, a solver, and then a linear retrieval map. The exact same thing is what you need to do code generation. And that's something we've been working on recently. And we've actually done this for a while, but now we have an alpha version of this. It's called CVX PyGen. And what it does is it looks at your problem. It then generates extremely efficient data structures in C that would evaluate, do the canonicalization and the retrieval. And then you just shove in the middle an embedded appropriate solver. And then you're good to go. You're doing code generation. So that's actually pretty cool. Okay, so I'm going to make some, I'll wrap up with some conclusions, right? I think these are non-controversial. So basically, I think convex optimization and control policies, they're simple and interpretable. So there's no way you could say that they're not. We know how they work. I mean, maybe there's not an analytical solution, but we know exactly how they work. They're not going to do anything crazy. They gracefully handle constraints and changes and failures. I think that's actually a huge benefit, even in cases where it doesn't actually work any better than, for example, when a person is driving or something like that. This is actually a really good thing to have. You can add safety fencing. That's very cool. And they can be effectively tuned quasi-automatically. So that's kind of it. And I guess there are now or soon will be high-level tools to design and implement these controllers, right? So I think these are kind of non-controversial. This one might be, and let me explain. So what I'm really saying is something like this. So I think of PID, by the way, with respect and affection, okay? And what it is it's an unbelievably simple control policy, if you think about it. Like I remember when I explained to people who've never heard about it before, they're like, that's it. And I go, that's it, dude. That's the whole thing. Like, that enabled the Industrial Revolution and like, 80% of all the controls that actually work around you are running PID. And they're like, really? And I'm like, mm-hmm. Yeah, so anyway, I say this with respect. It is a simple control policy. It doesn't pretend to optimize anything or to be the best at anything like that. It uses unbelievably simple models, if you think about it, right? So here's the dynamics model for PID. If you turn this knob up, the output will eventually go up. There. That's the dynamic model, okay? And you don't need anything else. That's all you need, right? By the way, if it eventually goes down, you just change the sign and everything's fine. So, okay. So the point is, it's like a workhorse. It's like a really good thing that you could just use, right? Oh, by the way, not coincidentally, if it's properly tuned, and there's like awesome books from like 1905 on PID controller tuning, which is very cool. Okay, so my claim is just, making a convex optimization control policy. If I was going to make a controller for something, I mean, if it's wildly nonlinear or something like that, fine, it's not. But in most cases, I'd come up with some simple form, come up with some reasonable thing. I know it's not going to do anything crazy, and then I would tune the parameters. And I'd safety fence them so the parameters don't get weird or anything like that. And my guess is it's just probably going to work, right? Could you do better with something fancy? I mean, probably. So, all right, so I'm going to quit here. And if I timed it right, we actually have some time for questions.
Great. All right, let's thank Steven. We do have time for some questions. Controversial questions are especially appreciated.
Yes, especially controversial, please. Really? No one is going to ask, why not just train a deep neural network? Seriously? Come on, someone once asked that question. Are you willing to do it?
Yeah, why not just train a deep neural network?
Oh, thank you. Thank you. That's an excellent question. Thank you. Yeah, so that's a great question. Actually, I think that deep neural networks play super nicely with these. Okay, so for example, in these things, you saw things like MPC and stuff like that. You need forecasts. Where are those going to come from? Well, honestly, we can make some pretty good forecasts with simple things. But sometimes a deep neural network is going to be the best thing. So what I would do, I mean, here's one, for example, in finance. This is a reasonable architecture, and I think it makes sense. You have a deep neural network that's looking at all Twitter feeds or some garbage like that. And then what it does is from that, it emits forecasts of returns, volumes, volatilities, okay? That goes into a very simple convex optimization solver that then emits a trade list. That is that's a good architecture in my opinion, and it works really well. Now, let's take your idea. Like probably once a week, somebody says like, oh, no, we're gonna go end to end, man, end to end. We're going from Twitter feeds to trade list. Everybody got this? And it is tempting. I mean, I can see the appeal of it. It's so seductive, and it sounds like, yeah, man, like, yeah, like my raw sensor signals to ailerons, right? So, anyway, you should be very happy if you flew here or intend to ever fly again. That's not how airplanes work, by the way. Anyway, it makes no sense at all to do this. If you've got this beautiful technology that can actually say thank you for your forecasts, I'm going to come up with something reasonable that balances all these things, handles the constraints and all that kind of stuff. Why not use it? So anyway, that would be my comment. Anyway, thanks again for the question.
Thanks for the excellent talk. So I have a question about hierarchical optimization problems, which we encounter in day-to-day life everywhere. Mm-hmm. So what is the best way to model it, and can you model it as convex optimization problems?
Yeah, so the question is about hierarchical optimization. I mean, if the things you're solving are convex, then yeah, there's extremely good ways to do that, right? You should actually, it's kind of interesting, right? Because, the tradition in engineering is actually just to have it be one way, right? You have a high level, a flight management system says that's your heading, that's your altitude. That goes down to a lower level thing that plans stuff out at the 10-second framework. It's the same in energy, right? Like last night, I mean, it's kind of hilarious that we're here, but whatever. Last night, the Cal ISO, planned out, how much power each generator was supposed to make each day. And then that's just marching orders. That goes down. But then real time, it changes in real time, right? So I mean, just if you do hierarchical is better. That's when the layers, that's a top down. When the layers talk back to each other, that's hierarchical. That's interesting. So, and there's super good methods for doing that. And I think there's a lot of people here who would know about some of these. I mean, just simple ADMM would do that, right? That's where, I decide at a high level what to do. I hand this off to, Manfred and Claire, and they work something out. And then, in fact, there's a discussion. That's actually the right way you should think of like ADMM. And they say, oh yeah, well, if you asked me to do that, here's what I would do. And it wouldn't be exactly what I asked. And then I would say, oh yeah, okay. And then I would update some things. I'd give them some new things. And then eventually we'd get bored, and I'd flip a bit in the packet, and the packet would say, done, no more discussion, negotiation over, Manfred, do it. That kind of thing. So anyway, good question.
What's your take on reinforcement learning for solving
great.
problems like this?
I didn't have to prompt. I was once again going to have to prompt that myself. Okay, so, what's that? Yes, of course. Well, I think for our online people, we want some mystery, right? But anyway, it's fine. Yeah. So the question is, what's my take on reinforcement learning? I mean, this was reinforcement learning. So, I mean, this is, an incredibly simple, this is the simplest thing you can get, right? And I think it's fine. So, a lot of the things I've seen seem too complicated and too fancy for a bunch of applications that I know about. I mean, and I'm just being honest, there's nothing wrong with thinking about it, I mean, and writing papers and doing research on it. But I think a lot of it seems like it's maybe, it can be used in the wrong setting, right? So, although actually, if you want, you could just call all of this reinforcement learning. It's just when we do when I'm envisioning doing this, these are simulations, so no one's getting hurt, right? That's the difference between maybe this and then actual like online learning and stuff. So,
I think there's time for one more question.
First of all, it's such an honor to meet Professor Boyd in person. So I'm Gary from General Motors. We love MPC, and we implement MPC in the powertrain control, which is already in the production. But when it comes to the vehicle dynamics control, vehicle motion control for AV application, one of the challenge of like implementing MPC is on the model side, because for vehicle dynamics, there's so much uncertainty. Even the uncertain is so uncertain. So it's
I'm going to use that from now on.
Yeah, it's causing a lot of like challenge when the software and the computation is not the problem, but the model, the interaction between the tires and the road, the slippery road, is giving us a lot of trouble when we try to use MPC. I want to hear your thoughts on that regard. Thank you.
Yeah, so that's, you brought up the critical part of robustness, right? And I remember I was around when, like robust control got started. And I remember this was like in the 80s, and I said, what's robust control? And they said, well, it's control where if the parameters vary, a controller where if the plant model parameters vary 1%, then it blows up or falls out of the sky. He said, that's called brittle or not robust. But robust control doesn't do that. And I'm like, I was kind of curious. I was like, wait a minute, sorry. That first one is that's not a brittle, it's a faulty, unworking, bad design. That's what it is. It's stupid, right? If your requirement is that things should work when parameters change, and the answer is, of course it is, then actually that comes into when you make that true loss function, right? So when if you use as your loss function here to tune things simply using these model parameters that are accurate as doubles or whatever, that congratulations, you're going to get something where you can do very nice simulations now. So, but actually a whole lot of that can be improved by simply making what you do. I mean, the simplest way is this: instead of doing one simulation with some control parameters, I'll do 100 where I sample from the parameters from their reasonable ranges. Like I'd say, what's the range of this thing? And they go, that's plus minus 5%. What about that one? That's plus minus 10%. What about, and then in finance, it's like they barely even know the sign of anything, right? So it's kind of, so you should do, so a lot of robustness is gained in the tuning, I think. Then I'm not averse to people embedding it in the controller, like the multi-forecast thing. But the truth is, a lot of times you don't need that. But when you tune it, you better know about robustness.
Great. All right. Let's thank Stephen Boyd.
Good. Thank you. Thanks very much. Thanks.